Sriram, who will be speaking on calculus and Bhaskar's Graha Ganitadhyay, the rates of motion of planets and their stationary points. Just a very brief introduction. Professor Sriram did his PhD in physics from IIT Kanpur and has served at the University of Madras, from where he retired as professor and head in 2011. He's currently with the K.V. Sharma Research Foundation in Chennai. He's been working in the field of Indian mathematics and astronomy for 34 years and has published some landmark papers on Indian astronomy and mathematics, and 3 important texts on the Kerala School of Astronomy and Mathematics, the Yukti Bhasha, the Tantra Sangraha, and the Karana Paddhati, with co-authors, and also a book very recently on Siddhanta Shiromani, the major work of Bhaskaracharya, with co-authors. And he's working on 2 Kerala texts of astronomy. He's a fellow of the Indian National Science Academy for his contribution, elected a fellow for his contributions in astronomy and mathematics.
Yeah, I thank the organizers for giving me this opportunity to give a talk. So it will be some kind of a physicist point of view, I will say. Okay, so it is the calculus in Bhaskara's Graha Ganitadhyaya, rates of motion of planets and their stationary points. Professor Bhargava did talk about the calculus aspects in mainly the infinite series for pi and things like that. But there is another aspect which came in India and we developed in India earlier, about rates of motion and all that. And so I am going to talk about that. Now, the very important thing about the motion of planets, which became important much later also, is the non-uniform motion of planets. Okay, it is fortunate that all the planets and stars and all that don't move around the Earth at uniform rates. We know that the planets move around the sun and even sun is not the center. Okay, and as it appears from the Earth, the motions are non-uniform. This non-uniformity of motions, plays a very crucial role in the development of physics, first astronomy and then development of physics. In fact, trigonometry and calculus come because of the non-uniform motion of planets. I mean that they are not going at a uniform rate about whatever, around whatever. Okay, so we had these epicycle models, probably borrowed from Greeks, but that is not clear from where and all that. But it may be possible. So essentially, what is happening is that the planet is moving in a circle. You say, suppose it is moving uniformly, so that in a big circle, that is the planet is at P0, let us say. So the big circle is called Kaksha Vrutta. Now draw a small circle called Manda Vrutta or Manda Nichocha Vrutta with some radius Rm prime at P0 and draw a line P0P which is parallel to the direction of what is known as Mandocha or apogee. Okay, so then the real planet, the true planet is at P. Okay, the mean planet is at P0. So we have to find out the connection between them. So that is what it is. I will not go into all these things, but basically theta 0 is that gamma O P0, that is the mean longitude, and then there is a correction, and the true longitude is gamma OP. The difference is, sorry, क्या हुआ? That's all. Okay. Okay. So the difference between them is, this is called Manda Sphuta, the true planet, and there theta 0 minus sine inverse of thing, and so is approximately equal to theta 0 minus Rm by R sine m, where Rm is the radius of the epicycle and R is the radius of the large circle. You see. So this is where trigonometry comes into the picture. This is why trigonometry was actually developed, both in Greeks and in India. But Greeks had these full chords and how to convert arc to chords and chords to arcs and all that. Whereas India had the real equivalent to modern trigonometry was developed, as emphasized by Professor Bhargava. So modern trigonometry, Aryabhatta was the first to talk about it. So the sine function comes here because of the non-uniform motion of the planet. So this is the thing, okay. And he also emphasized the fact that sine is a function, okay. Sine was used as a function in Indian astronomy, okay. So in the case of sun and moon, this is the one big circle, one small circle will do. For actual planets, there is one more correction. We will discuss that shortly. Now, it is natural for Indians to think of an expression for the rate of motion of this, this. So you have given the longitude as a function, okay? The position of the planet as a function, which involves the sine function. And what is the rate of motion? What is the rate of change? So it is natural for them, to Indians, to think about it. Whereas in the Greek astronomy, it is more complicated because you are giving some geometrical model and you are always converting, arcs to chords and chords to arc and all that, okay? So the rate of motion wouldn't have been very simple for them. So Indians, it was, because it was very much there and they had to grapple with it. And this is what is given, from the time of Laghumanasa of Manjulacharya around 10th century. So this is the kind of a thing, that if you find out this is the formula for the longitude and the rate of motion. If you differentiate it according to, the simple +2 calculus, so you get this, So essentially, it is, involving the derivative of the sine function as cosine function. So this was given, you see. Not exactly by Manjula like this, but afterwards Aryabhatta too gave this, and this is the kind of. So the concept of derivative was not, not in the sense of, what we have today, that, if you have, y and then y0, y minus y0 by x minus x0, take the limit, not like that, but they had the correct concept, when the time interval is small, how does the longitude change? So that is, they could formulate it properly, and this is what it comes. So this involves the recognition of the derivative of the sine function as a cosine function. So this is, of course, as I told you, it was there much before Bhaskara, and Bhaskara Siddhanta Shiromani is in 1150. So he
sleep time has to be increased.
Yeah. Yeah. So he explains in the detail what it is, what does it mean, this kind of a change in a small interval. So he calls it the tatkalika gati, this is precisely the instantaneous velocity. So the concept of instantaneous velocity was considered a very crucial factor in the development of mathematics in Europe, right? Newton and Leibniz and so on and so forth, you see. So instantaneous velocity was, is what, Bhaskara talks about it. So earlier scholars might have given the formula. He explains in his detail in his Vasana Bhashya, in his commentary. So that is the importance. So this is for sun and moon, it's simple enough. For planets, we know that, now we know that they actually move around the sun. So, but we always observe from the earth, okay. So you have to, there will be one more correction, basically. It is formulated that way, that is how they talked about, okay. So I will not go into the details, so you have to draw a diagram like this, and then find out the true longitude of the planet, okay. So just as there was the concept of a mandocha, so that one called a shigrocha, which is there, and then the true planet, you see. So the mandasputa, which I talked about, that may be a G with respect to Earth, and the true planet is at P, and the formula connecting between them is theta T is theta ms plus that formula. So don't bother about the details of that, but remember that it has a numerator which is sine function and a denominator which is the hypotenuse, the distance between E and P. So this is the formula for the true longitude, and this is what is there in Indian text, in varying details. And the difference between this theta shigrocha and the mandasputa, so that is called the shigra kendra, and the correction itself is called the shigra phala. So this is the formula, little more complicated than what we had for sun and moon, because planets are actually moved around the sun. But of course, it is not stated as such, only Nilakanta Somyaji states it later, okay, but this is what is implicit, you see, and it should have been implicit, otherwise they wouldn't have got the correct thing, you see, unless, you know, this implicit thing was, it was the fact was taken into account in the formula, they couldn't have predicted the planets' positions, so it was there. So this is the formula for the longitude. So now you have to find the rate of motion, you see, it's even more difficult, you see. So we have to take into account the time variation of this, the numerator, that is, you know, even if you take, yeah. So there's a numerator and a denominator, and of course sine inverse is there, okay. So even if you take the sine inverse to the other side and, you know, do that, but still there's a numerator and a denominator. And Bhaskara didn't know how to handle it, and even earlier astronomers also do these things. So we have to somehow deal with it. So he says the following in his Vasana Bhashya, Nahi Kendra Gatijameva Phalayorantaram Syat Kintu Anyadapi. Okay? So the difference in these Shigra Phalas, that is the correction, is not only due to the variation of this, what is known as the anomaly, you know, solar and Kendra Gati, but also to some other factor. The result obtained by dividing the project of Trijya and the difference between today's and tomorrow's Buddha Phalas by today's Karna would not be the one obtained by dividing by tomorrow's Karna. So what he is saying is that, basically, that, you know, what you take for the denominator, you know, even if you differentiate the top, for the denominator, what do you take? Do you take the today's thing or the tomorrow's thing? You see? But that may be difference is small, of course. But I said, even if the difference is small, the error would be high. Okay? So, because of the largeness of the numerator, bhajyasya bahutvat bahuvantaram syat iti etadanayanam hitva anyan mahamati madbihi kalpitam. Okay? So, because of that, some other method was, you know, thought of by some great intellects. You see, he doesn't mention who, and he doesn't describe, you know, who did it and, you know, how exactly they did, but it goes around, you know, explaining it himself. Okay. So he says it is said that only the rate of motion of the Kendra is corrected. Okay. So Kendra gatireva spashtikruta. Tasyami shigrocha gatehe shoditayam grahasya gatihi spotayeva avashisheta iti. So this, when subtracted from the rate of motion of the shigrocha, would give the true rate of motion of the planet. Okay. So what you have to, you know, if you are baffled by all these terminologies and these things, don't worry. I mean, mainly this is a little bit of complicated situation. So he is saying that, you know, the old methods will not work. To take the, you know, Mandaka Sputa and then make the one more correction and take the rate of that, that doesn't work. You have to think in a different way. You see, that is the very, you know, the greatness of Bhaskara. In many places in his text, he will say that, you know, so this is the things that are there, but sometimes you have to think in a different way. You see. So that is where this scientific nature, you know, comes out very clearly. So he gives a very ingenious geometrical construction for the this rate of motion. It is exact in his own framework. You see, I mean, it may not be exact expression as in the modern times, but whatever he had formulated, this is the exact expression. You know, it looks very different. Okay, from what we would have expected if using the earlier kind of a method. Okay. So, sputagati is shigrocha gati, okay. So, he is not making a correction to the so-called the mandasputa, which is one correction has been taken, and then you take the next correction. He is not doing like that. He is taking the shigrocha, the second important ucha, and you make the correction to the gati of that, and this is the expression you get, okay. And precisely he gives that formula, you know, delta theta t by delta t. Is this kind of thing. Though he may not use this, obviously he has not used this notation, but clearly say this thing. Okay. So this is the rate of motion. So now the very interesting thing, which is absolutely different from the sun and the moon, is that this can be positive or negative. You see. So when this rate of motion is greater, this is called a direct motion, and when it is negative, it's called a retrograde motion. And when it is zero, it's called a stationary point. Okay. So at the stationary points, this theta t, the true longitude, has a maximum. So and then there's a transition from direct to retrograde motion, and then it goes to a minimum, and then it goes from a retrograde to direct. So this will be, if you plot the diagram in the sky, it will be something like this. Okay. Don't think that, you know, this kind of diagram will appear in the sky, and this is a composite kind of diagram, you see. And to develop this kind of thing, just to know this, it takes not centuries, several millennia, okay. Not only, you know, Egyptians, Mesopotamians, Greeks, Indians, all many major civilizations, you see. It took a lot of time to even figure out these things, because if you just observe planets and all that, you know, and even if you are a keen observer, okay, it will take several centuries to actually get the pattern, and that is what happened. And this is a pattern you will get, and this is the diagram that is given in many textbooks related to this astronomy, old kind of astronomy. I mean, it is modern but old. Old means, you know, 16th to 18th century. That's called a modern astronomy, old period. Okay. And if you plot the longitude versus time, you get that right-hand figure. Okay. So the longitude will keep on increasing. So like in sun and moon, it will keep on increasing. It will go on and on, not at a uniform rate. But here it will go up, reach a maximum, and then come down. The slope will become negative. Okay, that is called Vakragati in India. Okay, Vakragati in Indian text. So that is a retrograde motion. So yeah, no, I don't. Yeah, so Vakragati is there, and then it becomes direct again. So this is the pattern, retrograde motion, and this is what is, you know. So in fact, some time back I was in some conference and all that. I was talking with some in India only. Somebody was, you know, science promoter and all that, you know, and we were discussing this Indian astronomy and what they did and things like that. So I said a lot of things were there, and you know, I was telling it briefly. So he said, retrograde motion? Yes, retrograde motion. Okay, and he gave a formula for that. You see, that is what is crucial. Yeah. So this is the retrograde and direct motions are there, and when it is zero, it's called a stationary point. Okay. So you can find out using the same, you know, geometry and all that. I will not bother you with all the details of that. So you can get a formula for that. So that is the formula. Stationary, when the Shigra Kendra has, you know, cos of that has this kind of a thing. This is the expression for that, where this RS is called the radius of the Shigra epicycle, and this N0, NS are the rates of motion of the, you know, planet and the Shigrocha. So things like that. So this is the formula. Actually, Bhaskara could have given the formula. He could have got it immediately from the expression he has derived. He could have got it in 2 steps, but somehow he has not given it. But certainly he would have, you know, had it in mind, because afterwards he will give the figures, the values, you know, for the various planets, the stationary points, and that precisely they are whatever we get from this formula. Okay. So here is the Manda Shigra Kendra. So how it is varying? So the horizontal line corresponds to this Shigra Kendra 0. So when the planet goes up to some point is direct motion. Okay, that P0 to PR1. So then retrograde motion, and then again direct motion. And where these are situated, stationary points are situated, so they are the stationary points. Okay. So these are maxima and minima. Even it is known that Bhaskara knew about this maxima and minima even in earlier context, you know. So I mean, imagine it is 1150. The year of composition of Siddhanta ceremony is 1150. So he is talking about maxima and minima and that kind of a thing. Even in those days, you know, we think that it is 17th century, 18th century. Okay. Okay. So the stationary points, as I told, he has not given the formula for that, but must have been aware of it, and is apparent from the value of the stationary points he is giving in his Grahaganita. We know this, all these parameters are there, he has listed, and if you compute it, you will get these values in that column, computed value of stationary points, and the stated value is this. The Bhaskara says that the stationary point of Mercury is 145, and again 360 minus 145, it will become retrograde to direct and things like that. So these are the values he gives. These are stationary points. Okay. So now stationary points are there in modern positional astronomy also. Okay. So this, for instance, is the figure I have taken from a very nicely written book called Astronomy Principles and Practice by Roy and Clark. Okay, so here S is that the sun is the center. He is of course taking the heliocentric model. So Earth's object is the small circle. The superior planet is the big circle. Superior means the whose orbits are larger than Earth's. Okay, they are called external, exterior, or external, or superior. Okay, and then Mercury and Venus are called inferior and interior. Okay, their orbits are small. Okay, so this as an example, he has taken this superior planet and find out the stationary points from entirely different considerations. Okay, so Bhaskara is direct, and he has given this thing the method. Here is Earth is there, planet P is there. Okay, and then you draw a line from Earth to planet. Okay, so he says that the stationary point is when this tangential component of the velocity is 0. Okay, only the radial velocity is there. So that is the thing, and then he gets the theta, and it can be translated to this stationary point, I mean this Shigra Kendra. So this is the formula. Okay, a to the power of a and b are the radii of the, it takes uniform, I mean the circular motion for sun and Earth and planet around the sun. So a and b are the radii of these orbits, and this is the formula. Cos theta is this, and even our terminology, it will become, I can write it like this. Essentially, cos of the sun minus the planet will be having this formula. Now, this a by b in Indian formulation is rs by r, Shigra the radius, and divided by the trijya. And Kepler's law, if you use Kepler's law, you get there is a relation between the distances and the time periods. Okay, you remember that Kepler's third law, t squared is proportional to r cubed. Okay, so using that you get n0 by ns is this, and you get precisely Bhaskara's expression. Okay, so that's very interesting. Bhaskara has obtained this expression. The formula is there, follows from what he has written. Okay, and this is very in a very entirely different kind of a. This is not really many people, even some great Indian scholars have not realized that this is the method for finding the stationary points in India. Whereas they take this, that whatever approach I talked about, from Roy and Clark and all that modern astronomy. So this is the stationary points. Okay. Of course, Bhaskara gives some definite values for them, but actually you have to take this correction due to eccentricity for the planets. Okay, that also has to be taken into account. So then the formula will become like this. It will become slightly changed. For instance, for this Mars and all that, you have to replace n0 by n0 prime. N0 is the number of revolutions of the planets in Mahayuga. Okay, it's called Bhagana. Okay, that Bhagana has to be changed to, you have to add one factor. You have to multiply by a factor which involves the correction due to the eccentricity. Okay, correction due to the ellipticity, as we call them. Okay, so that's it. Now, stationary points are not fixed values, but it depends upon time. Okay, so this is okay. So, and for Mercury and Venus, you have to do something more. Contrary to many opinions of many people that Indian astronomy was static and all that, and particularly the views of many section of the Indian scholars. Okay. Some Western scholars may be more accommodating, but there are some these things. Okay, so there was this thing, how to add the correction due to this eccentricity to Mercury and Venus. It is different. Okay, and in fact that is what Neelakanta Somyaji did in his Tantra Sangraha. And so you have to add it to the you have to make it to the Shigrocha. Okay, so what is called Shigrocha? So as it is actually the mean heliocentric planet. So then it is that prime sits on this ns, not n0. Okay, so this is what you have to do basically. Okay, so you have to do it in a slightly different fashion for Mercury and Venus. You see, that is taking the revision of the planetary model by Neelakanta into account. Neelakanta Somyaji is a Kerala astronomer. We have also translated and explained his book Tantra Sangraha. Okay, so this is the you have to do. Okay, that is in 1500. Okay, so now how exactly to calculate? You have to find out the mean planet. So for that you have to know the number of days which have elapsed, from the Kali Yuga beginning to a particular day. So theta 0 is that. Okay, so for that you have to know, if n0 is the revolution number of planets, okay, and y is the Yuga Savana, the number of civil days in a Mahayuga. Okay, so by rule of proportions, which is mentioned, okay, the importance given to rule of proportions or this rule of 3. So then the number of revolutions you have in the number of the Ahargana days, so that is that n0 into a by y, and you have to take a fractional part because that multiples of 360 don't matter, you see, because when you go and measure the angle in a circle, you see, you take only the, many revolutions might have taken place, you take only the one number between 0 and 360. So that is that, and there may be some value for the longitude at the beginning of the Kali Yuga, so that's called Dhruva. So this is the Mandasputa, and similarly for theta S and Manda correction to Mercury and Venus. Okay. Okay. And from our earlier experience, we know that Tantra Sangraha values for parameters yield better results for the planetary longitudes than the values of other tech. That's how, in fact, we started our investigations in Indian astronomy and all that earlier. Myself with Ram Subramaniam and Srinivas. So we were doing, and we found that Tantra Sangraha values are, what is correct. Then actually it's a later date, and he was mindful of the this more accurate observations and all that. So that is the we take those parameters, and also the Manda correction is correct only in his district. Okay, so that is what we are doing. So we can say that what we are having is a Bhaskara Nilakanta computation of stationary points. Okay, so the parameters are the following. The number of revolutions of Mars, Jupiter, etc. in a Mahayuga, that is what is given. Okay, their Manda radius, epicycle radius, Shigra epicycle radius and all that. Okay, and Mercury and Venus you have to do in a slightly different manner. Okay, so these are the things. Now I can make the comparison with data. You see, that is what is very, I think is quite interesting. So there are data every year. Of course, there are almanacs produced by all countries. So ephemeris they are called. In India, it's one Rashtriya Panchanga is published every year. You see, there's one Positional Astronomy Center in Calcutta. Okay, so it publishes all these data about the every year, every day, what is the longitude of sun, this thing and all that, for whatever use people can make of it, for religious or whatever it is, see. So they give and they will give the Indian terminology, Indian way of expressing the longitudes also, they call Nirayana Graha. All those data are there. Of course, they are compared using, modern calculations, astronomical, but that can take it to be real. They would have, I think, used the computer programs, okay, and codes, the modern codes, which take into account all these modern, celestial mechanics developments, all these things and all that, and then so these the modern data, okay, expressed in slightly in Indian language, okay. So these are for instance, for the Mars, for the year, and this Rashtriya Panchanga is available. It will be useful for anybody, for the finding out about the Tithi, Nakshatra of any day, the festivals and all that, all those things are given in it. Okay. But the data are aggregated in the So now you observe this Mars, for instance, it gives the longitudes every day at around 5:30 in the morning. So 3rd December is 101 degrees, 51 minutes, 41 seconds. Then see, you can say that next day it is increased, but only a small amount, okay, 54 minutes. The next day 56, then 101, 57 and 6 December. 7 December 24, it is 101 degrees, 57 minutes, 58 seconds, okay. So it is kept on increasing up to this point. See, now it decreases. 8 December is slightly less, slightly less. 58 say 33 ho gaya. And next 57, 33, 56, 19. So it keeps on decreasing, okay. So this is the stationary point, and the retrograde motion has started. Okay, and till so I come to yeah. So February, if you come, that is still increase this thing. Now it's still decreasing. 23rd February is this 82 degrees 48 minutes 50 seconds, and 24th is this 82 48 23. So it's decreased. The next day is 48 41. So it increased slightly. Okay. So like that now it will keep on. So this is the first is it is increasing but slowly and slowly, and finally it reaches a stationary point and then start decreasing and reaches another stationary point, the complementary stationary point, and then starts increasing. Okay. So for those stationary points, we have calculated, you can find out the longitude of the sun and the planet and all that, and find out the Shigra Kendra and use the Manda correction. That's the Indian calculation. When you do without the Manda correction, from the stationary point formula you get that 163.1771 without the Manda correction. Okay. And for the Shigra Kendra itself, if you do it directly from a simple formula, you get 168.4748. Okay. Similarly, for the complementary, it is 204 196. So they are somewhat divergent. Okay, difference of 5 degrees, 7.5 degrees and all that. But if you implement this Manda correction, that is the correction due to the eccentricity. So on 7 December, this is the Manda this Shigra Kendra is 158.1362 by direct calculation. From the stationary point formula, it's 159.8885. There's only less than half a degree. And similarly, for the complementary thing also, there is the divergence slightly more, but it is 200.86 and 202.95. Okay, so substantial improvement and reasonable agreement. I mean, you are talking about something which is following from a theory, which was written in 1150 and then somewhat revised and modified by Nilakanta in 1500, and you are talking about the data, in 2024. You see, so still, so they are working well. Obviously, they can be made even better, but I will not go into that. Yeah. Similarly, Jupiter, again there are the same pattern is there. It decreases, but ever slowly. It reaches the stationary point. Okay, so that when the derivative is 0, then it keeps decreasing and all that. And so here it is, the agreement is better. Okay, the agreement is better. One way of calculating, that direct calculation of this so-called Shigra Kendra, you get 127.568, and from the stationary point formula, it is 127.2633. And similarly, for the other complementary this thing, it's 233.47 and 232.94. Okay, better agreement than in the case of Mars. So that is because the eccentricity is somewhat smaller for Jupiter. Similarly, Mars also, it is slightly more eccentric than Jupiter, but less so than the Mars. So it is okay. Okay. Not as good as in the case of Mars, but Jupiter, but it is somewhat in between. Okay. For the Mercury and all that data and Bhaskara-Nilakanta theory, you get this. So there is absolute chaos. Okay, without Manda correction, it is there is some 30 degree difference. Even with that, there is some 7 degrees distinct for one. And for the other, it almost breaks down, because that cos ms, the modulus that becomes greater than 1. Of course, we are having some rounding off errors and all that, So it's consistent with 180, you see. So there's a lot of quite bad, it becomes. Okay, the Mercury is problematic because it is very eccentric. Because the eccentricity is the largest for the, among the planets, Mercury is the largest this thing. People had problems. I think even Kepler had a lot of problems in Mercury, So it is not easy to observe and this thing. So it is in the modern way, one has to add some more terms, to otherwise to make it better for the longitudes. So we have to, and we ignore the other terms proportional to E squared and all that for other planets, but perhaps it is not, it is not viable to ignore these terms, for Mercury. So that is the thing, So that's why it is bad. But let's take the case of Venus. The Venus, the eccentricity is small, and the agreement is really striking, even without Manda correction, because the eccentricity is small. See, 167.2895, 166.78, this thing. See, the small half a degree is accounted for even, where do you take the stationary point? You see, I just listed every time beginning it is there. It may be in between also, no? So half a degree, this thing is understandable. So, in this thing also, other complementary pair also, this thing is small. With Manda correction also, it is okay, it's quite okay. And but one day it is okay, for other day, little not so good. Okay. So that is, of course, we have taken only one set of points. So some 1 year. So one has to do this thing, and maybe one has to do some more, define it using some different better parameters and things like that. So essentially, what I am trying to say is, they had this concept of this rate of motion, and they could even apply it to what is the planets and all that, where the rate of motion is a little complicated. I mean, that is even in 12th century they could do it, and with that we could get some tallying with data. Even in some modern data, more or less it is agree. So that is what is this thing. It could be improved. Yeah. So now I think I will summarize and conclude. So finding an expression for the true rate of motion of a planet would have been a challenging problem in 12th century. Bhaskara derives such an expression in his Siddhanta Shiromani using a novel method, which he attributes to scholars with high intelligence. Okay? And it is indeed a very interesting kind of derivation. Okay? And is ideally suited for discussing retrograde motions and stationary points, which are considered as some kind of tricky issues in astronomy of those days. And the expression for stationary points in modern spherical astronomy is another version. Actually, they can be related. That's what I have seen. Here they talk only about distances and velocity components and all that. Still, they can be, you can compare with them, and in fact you get essentially same results. And we have to take into account the equation of center and Manda Samskara in determining the stationary points. And also we have to go beyond Bhaskara's parameters. So Tantra Sangraha parameters were used by us, and Tantra Sangraha treatment of this interior planets Mercury in minutes. So you can say that we are considering a Bhaskara Nilakanta formulation of the problem. Okay. So that is, and that fares reasonably well. Not exactly, but quite okay considering the time gap between the theory and the data. So even with that, Mercury of course is still problematic. Okay. Now even with all these, in this Shigra correction, only mean sun was used in Indian text. So if you use the true sun, that is, make the correction to sun also, planet also and sun also, the correction due to the eccentricity or ellipticity orbit, it is possible that you may, in the improved matters may improve. So basically it is a sound technique, but because of the change in data, various parameters are not only inaccurate, they may change also a little bit. So all these, if you take into account, it is possible that you may get actually, we get reasonable agreement with data, but you may get it even better. Okay, so that is with a reasonably simple formulation of the problem. That is the message I wanted to. Okay, thank you. Okay. Yeah.
Thank you, sir.
Yeah.
for that fascinating exposition. I'll invite our next speaker, Professor Venkateshwar Pai, who's Associate Professor at the Department of Humanities and Social Sciences at the Indian Institute of Science Education and Research in Pune. He received his PhD in Indian Astronomy and Mathematics from IIT Bombay, and he works on the historical development of Indian astronomy and mathematics, especially the Vakya system, manuscriptology, and critical editions of primary sources. He's trained in a range of classical scripts from the South, and his major publications include editions and translations of texts like the Karna Paddhati and the ongoing Drikkarana project, which he's going to be speaking from today on Malayalam and Manipravalam traditions, textual traditions in mathematical astronomy. Sorry, just give me on except projection. Projection बंद करना है. अब एक सेकंड मैं इसको फुल स्क्रीन कर लेती हूँ. बंद कर दीजिए.
Hello. Good afternoon, you all. In the previous talk, Professor Sriram has talked about mainly about the Siddhanta Shiromani, so which forms one of the class of Indian astronomical literature that known as Siddhantas. So I will be talking about a text called Drikkarana, which comes under another class of Indian astronomical literature, which are known as Karanas. So Indian astronomical literature we can broadly classify it into two categories. One is Siddhantas and the Karanas. So what's the basic difference between them? So there are three major differences that we can think of. One is the mathematical complexity involved. Siddhantas are more mathematically complex as compared to the Karana texts, which are sort of practical manuals. And the second is the epoch that is chosen. So, Professor Sriram also talked about the epoch as Kali Yuga or the Kalpa, which are usually used by Siddhanta and Tantra texts. But in Karana text, the epoch would be chosen recently. It will be a recent epoch. Okay, so and the third difference is the magnitude of parameters that is used. In Siddhantas and Tantra texts, the magnitude of parameters are huge. Here, the multipliers and divisors which are used in Karana texts are less on the order of magnitude. So, Drikkarana is such Kerala astronomical text which comes from the name. It comes under the category of Karana text, which is it's kind of so this is we are working on the text from a primary manuscript which is obtained from Kerala University Oriental Research Institute on Manuscript Library. We have also two different manuscripts from K.V. Sharma Library and the University of Tübingen, which our study reveals that the both are transcribed from this particular manuscript, so they come under the same family of manuscripts. So Drikkarana is a unique text in several sense. One is it's the language used. Language used by Drikkarana is Malayalam. Again, of course, Yukti Bhasha is also Malayalam, but this is in the form of poetry. It's composed in the form of verses. And again, the Malayalam used is highly Sanskritized Malayalam, which is close to Manipravalam. And this is sort of different as far as the content is concerned. This is quite different from the texts such as Khandakhadyaka or the Karana Kutuhala or the earliest Karana text, that is Karana Ratna of Devacharya, in terms of the contents, because this is again more close to a Tantra text. When we look at the distribution of topics and the contents, it's in both in the terms of contents and the magnitude of the contents, it's close to the Tantra text. But the author calls it as a Karana text, and it's again it serves the purpose of the purpose of the text is Driktulyam Karanam. He explains it as in the one of the verses as Driktulyam Karanam. It is in accordance with the observation, which means are there Karana texts which are not related to observation? Because Karana texts, as I mentioned, we have two categories. One is Siddhantas and Karanas. Karanas are practical manuals, and Siddhantas mathematically complex texts. And we can actually, they follow some, we can actually derive any Karana text from a Siddhanta text, which is Karana text is a miniature or simplified version of a Siddhanta text. So we can actually derive, and the text which talks about the Paddhati or the method for composing a Karana text are known, there are texts such as Karana Paddhati which talks about the method for composing a Karana text from Siddhantic text. However, the Drakkarana is composed based on the real observation. So now, in the first chapter, he talks about the audience are Balas. Balanam Ganita Prakaramarivan Chollunnuyan Bhashayai. So Balanam, here Bala is as a child, and again in Indian Shastri context, Bala is Grahana Dharana Patuhu Balaha. So one who is capable of observing and retaining the information is known as Bala. So the audience is for the text is Balas, and Chollunnuyan Bhashayai. Bhasha here refers to the local language, the local Dravidian language, but when we analyze the language is very close to, highly Sanskritized, and the composition is close to Manipravalam. Now what is Manipravalam? Manipravalam is a blend of two different languages. There are two terms here, Mani and Pravalam. Mani is ruby, and Pravalam is in Dravidian language, it is Pavidam, which is coral. So it's blend of Mani and Pravalam using a thread, red thread. Red thread represents the aesthetics, and Mani represents the Dravidian language, that is the Bhasha, and Pravala is Sanskrit. So based on the composition, so it is blended in, and you can see that Mani, that is the coral and ruby, is in red in color. So it's blended in such a way that you cannot really distinguish that they are blended. So it's based on the composition. So again, the Leela Tilakam, that is 14th century text in Sanskrit, which describes the Manipravalam language, it's the grammatical structure and so on, where it divides the Manipravalam into Madhyama, Uttama and Adhama and so on, where it gives importance to these two languages, is the Bhasha, then the Sanskrit, and the thread, which is red thread, which is the aesthetics. But in astronomical and mathematical context, we cannot bring aesthetics into picture. So one has to compromise on that aspect. So you cannot find aesthetic beauty as in the case of normal literary text. So this could be, the kind of Adhama Manipravalam, or there are again 8 divisions of Manipravalam which is mentioned in the Leela Tilaka. In the same context is this particular text, Drakkarana, which actually composed in different meters or chandas. Interestingly, if the complex mathematical ideas are composed in simple chandas such as Anushtup, and the complex chandas such as Chardula Vikridita or the Malini, etc., are used for explaining trivial things. And also we can find so much of repeated mathematical ideas, which are trivial mathematical ideas which are repeated. Complex one is very crisped, and he tells us to, he wants us to think more and do more job. we have observed this, again, this is not a conclusive statement. We have observed this in the case of Vasana Bhashya as well. Trivial concepts are repeatedly repeated several times, whereas the complex contents are not repeated. So that's again. Now, who is the author?
Needling the audience.
So now.
Modern maths paper.
Uh,
You can discover, easily prove they're right.
Sure.
So now the time of composition is very clear from the text. So there are 10, the text contains 10 chapters, and there is this very small chapter of 7 verses which is known as Upasamhara Adhyaya, where he clearly mentions that column B, Bahisuno. Bahisuno is a number which is in Katapayadi, which is it corresponds to 783. Column B is the Kollavarsha, that is the year used in Kerala, so which corresponds to AD or 1608 CE. And this is the explicit evidence of the time of composition of the text, and we can also find the time of the composition from implicit in an implicit way, that is, the khanda, there is something called Vakya system, and using the Vakya system of computing the position of the moon or the longitude of the moon, there is a term or there is a concept which comes into picture, that is khanda. That khanda given by the Drikarana author is Putran Dhatu Nrasaukhyonu. So that corresponds to 1706,821, which is the number of civil days elapsed from the beginning of Kali. So which corresponds to, again, we have to add some factor x, and that is the rate of anomaly. Number of days in rate of, corresponds to rate of anomaly. So we can come up with these 4 dates, which also correspond. One of the dates correspond to January 20, 1606. So it's very clear that this also matches with the previous date 1608. Again, this is based on the observation as the author. So it's Saukyo Nu. It's he actually.
Also you had this 783.
No, Bahisu now.
Bahisu.
No, zero. That okay. No, is it number way or linguistic or the okay. Here also Saukyo Nu is 0. Yeah. Nu is 0. Yeah. Yeah, so that it's actually 01706821, but 0 is mathematically irrelevant here. So yeah, so 17. Okay, I was thinking that linguistically you are asking. Okay, I was thinking it's.
Also, I was just thinking.
Yeah. But no, for of course to fit the meter. Yeah, yes. Putram Dhatu Nrasaukhyonu in Vangur Kalyana. Okay, so now he actually. So the name of the text itself is Drikarana, and we already mentioned that it's based on the observation. So what is the time period of the observation? It's also given by the person. Jasustaveti kalyabde tularnar avanitale paschimam bhoditiratta ninnu 30 varshavam nokitu ganakanmarum janasevanu vatsare. So there are 30 years of observations made by the Ganakas, and then he composed this text based on that. Okay, now the authorship. There is no mention of author anywhere in the text. So the Charles Wish in his paper on Madhava series, which is published in Royal Society, he mentions this major 4 texts, Karana Paddhati, Tantra Sangraha, Ganita Yukti Bhasha, and Sadratnamala. He also mentions this text Drikarana, Wish attributes the authorship to Jeshtadeva. Again, K.V. Sharma, based on various factors, he also attributes it to Jeshtadeva. So we are not sure. Again, the way the text has been composed, we think that cannot be Jeshtadeva, but it's not a conclusive statement. So we are in a confused state now whether it's but the Drikarana text does not say about authorship. Yeah. So now what is the purpose of the text? So here in the first chapter, the author clearly mentions about the purpose by giving some historical account. So again, the Kalyabdantra Sahasratil Paranjannulla Nalila, Uttuvannidumarilla, Grahanadigalunume, Karanangalumuttida, Siddhantangalumuttida, Tada Hyaryabato Nama, Ganakastad Abhavat Bhuvi, Jnanatungedi Kalyabde, Jatana Yavanitale, Giritungedi Kalyabde, Ganitam, Nirmitam Param, Shastram, Arya Bhattiyakyam, Tasmin Paryaya Muktavan. So in this first he talks about the Aryabhata who has born during the 3000 Kali, and during that point of time the observational results were not matching with the computational value. So he, the astronomer called Aryabhata has composed a text known as Aryabhatiya. Then iti nischitya palarum acharichavanitale Chirakalam Kadinyapol Nikam Valare Vannidu. So after some point of time, again there was a deviation from the observational results. Then Ranga Shobhanu Kalyabde Kaschit Vipravarastada Paschiman Bodhitiratta Noki to Vechada the Dwadashabdam Kadinyitta Tantra Sangraham another Tasmin Paryayum Pinne. So before this so he talks about Tantra Sangraha also explicitly. Before that he talks about the Drigganita, which is composed in 14th century. Before that he also talks about the Parahita of the Haridatta in 7th century. Okay, and then finally what he says is Paschimam Bodhitiratandu 30 varsham nokida Ganakanmarum Janasevanuvatsare Sukshmam Varakti Nirmichal Ganitagamam Mannavar. So he is again referring to this particular text Drikkarana. Iniyum kandu kolleyanam chirakalad varunada. So and again he tells that okay, one has to again compose several texts based on observation when you observe discrepancy between the observational and computational results. So now, Drikkarana is divided into 10 chapters, and the first chapter of course talked about the revision of parameters based on observation. Then in second chapter he also gives his own parameter which he has constructed based on the observation. So this is the parameter given by him. These are the number of revolutions of the sun, moon and other planets in a Mahayuga. So now we can also just put it, so whatever the text he has mentioning, Aryabhatiya, then Parahita, then Drigganita, then Tantra Sangraha. Then after Tantra Sangraha, he gives his own set of values. So now here we have just put these are red and blue color. This blue color, these data are reconstructed from the text. But these texts, Parahita and Drigganita, they are proper Karana texts. It's also again Parahita is not a text name. It's it is a system. So it's a Parahita system by or Parahita Karana by Haridatta. The text name is Grahachara Nibandhana and Grahachara Nibandhana Sangraha. So they actually behave like a Karana text, and they give the smaller multipliers and devices. From those smaller multipliers and devices, especially from the rate of motion, we can actually reconstruct these values in Mahayuga. So Drigganita also gives the same, but the Drigganita also we can construct two set of values. One is by keeping the sun's revolution and the number of civil days constant, and other set of values we can construct by just keeping sun's revolution as the same, that is 43,20,000. Then we also get a different value for number of civil days in a Mahayuga. However, this Aryabhatiya, Tantra Sangraha and Drikkarana, they give these values explicitly. So that's why what I'm telling is Drikkarana, though it is a Karana text, it actually gives number of parameters like in Siddhantas and Tantras. Okay, again, now what is Tantra? Tantra and Siddhantas we cannot actually differentiate. They are almost similar. The broader classification is Siddhantas and Karanas. Then again, Siddhanta, in between we have Mahatantra and Tantra that are more closer to Siddhantas. And then we have another text called Vakya system, which is more again closer to Karana text. It is a Karana text only, but using Vakyas. But Parahita and Drigganita, again, they are different Karana texts as compared to Devacharya's Karanaratna or Khandakadika or Karanakutuha, because they are also composed in sort of Vakyas, because you will find all the Mandajyas, Shigrajyas of planets, and so on. Again, we will not find any kind of algorithms as such that we find in Siddhanta and Tantra texts. However, again in Drikkarana, we find lot of innovative mathematical ideas which are found in other Siddhanta texts as well. So in this today's the next part, the next half of my talk would be just briefly explaining those two such mathematical ideas which are explained in which we find some sort of development from the previous texts. One is nearest integer continued fraction. So the continued fraction in Indian context is known as Valyupasamhara. So the Valyupasamhara technique or the continued fraction is implicitly used by Aryabhatta or Brahmagupta or Bhaskara to solve indeterminate equations or the Kuttaka problem. But explicitly we find this in the Karana Paddhati, and there are two types of Valyupasamhara method, Valyupasamhara 1 and Valyupasamhara 2, which are defined to describe to find the successive approximation of two ratios of large numbers, successive approximation to a ratio. Okay, so now we also find the similar words in Drikkarana. We may sometimes feel that it is completely translated from Karana Paddhati. Definitely the author might have gone through Karana Paddhati. The text, this Drikkarana text is closely related to Karana Paddhati, related to Karanottama, related to Dirganita, related to Parahita Ganita. So even Tantra Sangraha, he also tries to touch upon some of the spherical astronomical problems which are found in Tantra Sangraha text, but either we don't understand it clearly, or it's very crispy to understand, it's very complex to understand, or sometimes he makes some kind of mistakes in as compared to Tantra Sangraha. Maybe that's why he is trying to be anonymous, we don't know. So now Anyo, so this is similar to Karana Paddhati, but he goes one step further. Anyonya Chaivu, Bhudinam Padiyangalum, Palangale Kramatal, Anga, Adhodo Vechu Kondatha, Dhanarnatmakayulla, Gunaharan Vartuga, Swapurva Gunanignascha, Tatpurvena Sanyuta, Gunaharascha Jayante, Rupamadi Gunam Bhavet, Agre Paraspara Hruto Labdham, Purvaharam Smrutam, Paraspara Hruto Shesham, Yada. Twadardhadikam bhavet. So this is from the last two lines. That's the kind of small contribution by the Drikkarana author that makes the continued fraction nearest integer continued fraction. So this is the translation. Divide Bhudina and Paryaya mutually. There are Bhudina and Paryaya, that large two numbers. Divide them mutually. Keep the quotients aside. Keep the successive quotients. Suppose if I have A and B are two numbers, when I divide A by B, so I get a quotient called Q1, and I also get a remainder R1 that the divisor of this A and B, that is B, has to be again divided by this remainder R1. Then again we get Q2 and R2, and this process has to continue. And we have to store these Q1, Q2, Q3 values at a place, and we have to write down them one below the other. And above Q1 we have to place number 1. Okay. Number 1, and in the next step we have to delete this number 1, and Q1 has to be kept as it is. Q2 has to be modified as Q1 into, so in the second column, the third row would be Q1 into Q2 plus 1, Q1 into Q2 plus 1, and then Q3 up to Q1 has to be placed as it is. In the third column we have Q1 into Q2 plus 1, then the fourth column would be Q1 into Q2 plus 1 multiplied by Q3 plus Q1. And this process has to be continued. So finally what we get is the successive haras or the divisors as Q1 into Q2 plus 1, etc. Similarly, we can also independently we can find successive gunakaras or multipliers. Here the difference is you have to keep 1 and Q1, Q2, etc. By finding multipliers 1 below 1, we have to keep Q2, not Q1. So Q1 should not be considered here. Okay, and the rest of the process is same, and finally what we get is here is the first term would be, the first multiplier would be 1, then Q2, Q2 multiplied by Q3 plus 1 is the third multiplier, etc. So the G1 by H1 would be the one of the approximations. Second approximation would be G2 by H2, G3 by H3, and so on. So this is how the normal or the regular continued fraction technique works. So this is explained in Karana Paddhati. This up to the penultimate, till the penultimate verse, the Karana author also explains the same, and then he goes further, one step ahead. Paraspara hritau shesham, when you divide mutually, yada shesham means the remainder, yada tu ardhadikam bhavet, tada rupam phale yogyam shesham harat prathak sthitat. So if Ri is less than Ri minus 1 by 2, then Qi and Ri remains the same. And epsilon, so in this we have introduced a new term called epsilon I plus 1, that is 1. And however, if Ri is greater than Ri minus 1 by 2, that is the ardhadika, this is 1 by 2, then Qi has to be changed to Qi plus 1. So this is not in the subscript, it's actually Qi plus 1. So there is a typographical mistake here. So and Ri is Ri minus 1 minus Ri. And epsilon I plus 1 becomes minus 1 in this technique. So now suppose this is, suppose as an example, suppose if we, so this is the 24th row, suppose these are the two larger integers, and if we apply the regular continued fraction, these are the successive approximation that we get, and this cross sign you can see here. So here you have epsilon I plus 1 becomes minus 1, that is the ardhadika, here it becomes ardhadika. So and if you apply the nearest integer continued fraction technique here, so you have this is the successive approximation obtained by that. So this is the one mathematical development that that happens in this text, including other things. And the other is Professor Sriram again talked about the derivative aspect while explaining the stationary points. We Koti Phalagni, so that's the verse gives by the Bhaskara, where he talks about this derivative of sine function as cos in the rate of motion of planets. The Vikarana author uses this concept of derivative in a different context, known as Vyatipata and Vaidhrita. Vyatipata and Vaidhrita are two astronomical phenomena. So in order to understand that, we need to a little bit know about spherical astronomy. So here in this picture you can see that this great circle is equator, and the green circle is the orbit of the moon, and red is the ecliptic, which is the orbit of the sun. I mean the sun's annular motion happens. So now there is a term called declination or kranti in Sanskrit, which is nothing but the deviation of any object, celestial object, from the equator. So now the mathematical, so here if it at this intersection point, this at the intersection point with the equator, the declination would be 0, and it increases and reaches maximum here, again comes down and becomes 0 here. So now and the sun and moon, of course, they are continuously moving, so their declination changes. There is a mathematical problem here, is when the declinations of the sun and moon, the instant, so the instant at which, finding the instant at which the declinations of the sun and moon become equal. Okay, we can have several cases when sun is here, moon is also here, when sun is here, moon is here, when sun is here, moon is here, moon is here, sun is. So we have several cases. Based on that, he has divided this phenomena into two, that is Vyatipata and Vaidhrita. So the problem here is to find the instant of equality of declination between sun and the moon. So in this context, the previously till this instant of declination, that is the instant of Vyatipata, are found from the proportionality theorem, and using the iteration. That was the procedure that we find in other astronomical texts, but the Vikarana, he uses the concept of derivative to find this particular, to solve this particular mathematical problem. So I'm not going to the details. So this is the verse pertaining to the algorithm, that is Chandrande Kotija വേറെയെന്നങ്ങു വെച്ചത് വർഗിച്ചിട്ടതിലും പിന്നെ രവീന്ദ്രോഹോ ക്രാന്തിതങ്ങളിൽ കൂട്ടിത്തയോരന്തരത്താൽ പെരുക്കി സംസ്കരിക്കണം ചന്ദ്രകാന്തി കുറഞ്ഞീടിൽ കളവു കൂട്ടുകന്യഥ അതുമൂലിച്ചു കൂട്ടിയിട്ടു കോട്ടിജക്രാന്തിലിപ്തയേത് അർക്കസ്യ കോട്ടിജക്രാന്തിം ഗാരഘ്നം നരഭാജിതം ഫലവും കൂട്ടിയർദ്ധിച്ചാൽ ഗതിക്രാന്തി അതായി വരും. So first he talks about something known as gatikranti. Gatikranti is the rate of motion of the declination. So we till in Bhaskara we came across the rate of motion of the planets, that's the rate of the change in the longitude, but here the change in declination, which is used by the Gatikranti. So this is the expression which is given by which we obtained from these verses. From this Gatikranti we can actually find the instant of Vyatipata using this algorithm. I'm not going to the details. By using this algorithm, where the usage of cos function as a derivative of sine, without the knowledge of the derivative of sine function as cos function, we cannot he cannot come up with this kind of algorithm. This is the rationale used by him. Okay, thank you. Questions? Okay, thank you.
So thank you so much to our speakers. We'll close the session now. I'll just request Dr. Gopalakrishnan to honor both our speakers. Come. Professor Sriram.
Yeah, I think these are okay. No?
Okay, fine.
Thank you.
Lunch is served outside. If possible, we'll try to reconvene very shortly after 2, if possible. Yeah.
Maybe some time, otherwise
Right. 2:15?
2:10 is okay. Half an hour.
2:10.
2:10 is.
Thank you.